In this example problem, we have a car starting from rest, accelerating at 2.0 meters per second squared up a hill that is inclined 5.5 degrees above the horizontal. How far, A, horizontally, and B, vertically, has the car traveled in 10 seconds? Okay, so let's just start by drawing all of these, everything that we know about the situation on our picture. I've already started our picture. Now, keep in mind that this is not drawn to scale. I always draw things a little exaggerated just to make it a little easier to see. So, first thing I'm going to do is I'm going to draw my acceleration vector. So we know we're accelerating up the hill. So that implies that my acceleration is pointing up the hill. So that's my acceleration vector. And the magnitude of that acceleration, magnitude of that acceleration is equal to 2.0 meters per second squared. Okay, and we know that it is inclined at 5.5 degrees above the horizontal, which means that I'm going to draw just a horizontal line, okay, from my starting point. Okay, and the angle is going to be measured up to that vector from that horizontal line. So this angle here is 5.5 degrees. Okay. Now we also know about this problem that the car is starting from rest. Okay, so let's place our origin where the car begins. So right here where I would say the car begins. Okay, that's where we're going to define our origin for the position. So origin is here. Alright, so when the car is at the origin, my position x component is equal to my initial position y component, and they're both equal to 0. Now, when the car is starting at this position, okay, it starts from rest. So I also know that when the car is at the origin, that my v naught x is equal to my v naught y, and they're both equal to 0. Okay, because it's starting from rest. Note, it's the initial velocity is not 0 because it's starting from the origin. My initial velocity components are 0 because it's starting from rest. Okay, we also know how long in time that this car is traveling. So the whole goal is to figure out how far A, horizontally, and B, vertically, the car has traveled after the time 10 seconds. So I'm just going to make a note of this, that t is equal to 10 seconds. Okay, now for the way that we're solving all of these problems, we're going to be using this new method that we talked about in the previous lesson, and that is where we have to break all of our vectors into their x and y components. Remember that acceleration is a vector. Okay, so whenever we find the x and y components of the acceleration, that will be my x component for the acceleration and my y component for the acceleration. So here's my acceleration vector. I start by setting up my right triangle by just drawing a vertical line downward. Okay, draw my little 90-degree angle box. Now, because this side of my triangle is up and down like my y-axis, when I solve for this side, this is going to be the y component of the acceleration, okay, not the velocity in this case, okay, because this vector is acceleration, so when I solve for this side of the triangle, it's going to be the y component of the acceleration. Likewise, when I solve for this side of my triangle, okay, it's a left and right, like my x-axis, so that is going to be the x component of my acceleration. Now, it's just some basic trig to solve for both sides of my triangle. We'll start by doing sine of theta, which in this case is 5.5 degrees. So sine of 5.5 degrees is equal to the opposite side, so AY in this case, AY divided by the hypotenuse, which is our 2.0 meters per second squared. Okay, so divided by 2.0 meters per second squared. All right, now to solve for this, I just multiply both sides by 2.0 meters per second squared. So multiply this side by 2.0 meters per second squared, and then of course multiply the other side It's a little cramped here, 2.0 meters per second squared. Sorry, I'm kind of running out of room there. Okay. Now, on the right-hand side, my twos cancel out, and then I'm left with 2.0 meters per second squared times the sine of 5.5 degrees is equal to a sub y. Okay, plugging that into my calculator, I get approximately 0.191 meters per second squared is equal to AY. Now keep in mind, okay, now I'm not rounding this until the very end, but I'm just going to write it as 0.191 to help keep track of it. But when I type this into my calculator in future problems, I'm going to use that whole number. So if you typed sine of 5.5 degrees times 2 into your calculator, you probably got 0.1916915, blah, 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 blah. Okay, so you need to keep all of those numbers whenever you plug this into the kinematic. But for this, I just don't want to write all those digits out, so I'm just going to write the first three to help me keep track of it. Okay, now I'm going to use my cosine function this time, so I'll do cosine of 5.5 degrees is equal to, in this case, the adjacent side, so a sub x divided by the hypotenuse, okay, which is 2.0 meters per second squared, doing the same thing. Multiply both sides by 2.0 meters per second squared. Then multiply the other side by 2.0 meters per second squared. Okay, and then you can see that the 2.0 meters per second squareds cancel out on the right-hand side, and I'm left with just 2.0 meters per second squared times cosine of 5.5 degrees is equal to a sub x. Okay, now I'll just plug this into my calculator, and I get approximately 1.99. So 1.99 meters per second squared is equal to a sub x. Again, I'm not going to round this number until the very end. And when I plug this into my kinematic equations, I'm going to use every single one of those digits that are in my calculator. Okay, so now we just need our kinematic equations, which I have written on the next slide. Let's go there and take a look. Okay, so remember that all of our kinematic equations are broken into two. Okay, it's the same equation, except in one equation we're dealing with only y components, and in the other one we're only dealing with x components. You're going to hear me say this over and over and over again. You cannot use x components and y components in the same kinematic equation. Okay, so you can't mix up your y values with your x values. Now, one thing that I also need to write here is we know that the time is 10 seconds, okay, and because that is a scalar quantity, both situations are going to have the same time, so 10 seconds, t equals 10 seconds. Now, luckily in these two cases, we have a lot of zeros, so many of these terms are just going to go away. So if we start with the vertical direction, you've got y naught is equal to 0. Okay, so when I plug that in, you'll find that the first term just goes away. When I plug in the y component for the initial velocity, you'll find that the second term also just goes away. Likewise, for the x component, kinematic, okay, I know that my initial position in the x direction is 0 because the car is starting at the origin, so I'll plug that in. Okay, the first term goes away. And then I'll plug in the x component for my initial velocity into the second term, and that also makes the second term go away. So now I have some relatively easy equations to work with here. I know what my y component for the acceleration is. I'll just plug that in for ay, and I also know what the time is, so I'll plug that in for t. So let's go ahead and solve for that. So we've got y final, so that's going to be my vertical distance that I travel, is equal to 1/2. Okay, plugging ay in for ay, I get 0.191 meters per second squared. okay, times, plug the time in, and don't forget to square it. Okay, so 10 seconds squared. Now, plugging all this into my calculator, I get approximately 9.58 meters. Now, just keep in mind that if you got a slightly different number, that may be because you're just typing in 0.191, but I don't do that, okay? So the number that I'm actually plugging in here is the 0.19169150504 in for the acceleration in the y direction, okay? So keeping track of my sig figs. Right, I've got 2 sig figs for my acceleration, 2 sig figs for my angle, and 2 sig figs for my time. So watching my sig figs, this rounds to, okay, that rounds to 9.6 meters. Okay, so that's the distance that that the car travels vertically, and we know it's vertical because it's in the y direction. Okay, doing the same thing in the x direction, I've got x final is equal to 1/2, okay, 1/2 times, okay, AX, which we know is 1.99 meters per second squared, okay, now times the time squared, okay, don't forget that squared, times 10 seconds squared, and what I get when I plug all of this into my calculator, approximately, let's see here, 99.5 meters, so 99.5 meters, which watching my sig figs, that's going to round to 100. Okay, so 100 meters in the x direction. So that's going to be my answer to part A. Okay, so this car, after 10 seconds, travels 100 meters horizontally, okay, and after 10 seconds, it travels 9.6 meters vertically, so upward. All right, that's the end of this problem. If you have any questions, feel free to raise your hand and ask.